Hello Godotneers! In this second part of our particle systems video series, we're going to explore 3D particle systems. We're going to learn the basics of how particle systems work in 3D and how we can build effects like fire and rain. We'll have a look at particle attractors, how to make particles collide with the environment, and how to use sub-emitters to create more complex effects like rain splashes. This is a beginner to intermediate level tutorial. You should be familiar with the basics of particle systems in Godot that we have looked at in part 1 of this video series. You should also have a basic knowledge of the 3D parts of Godot, like meshes and 3D materials. And finally, we are going to do a bit of scripting, so you should have some basic knowledge of how to program with the GDScript programming language. For this second part, there is an updated version of the example project that we used in the first part. So if you want to follow along, please download the sample project from GitHub. There's a link to this project down in the description. In Godot, 3D particle systems are very similar to 2D particle systems. The main difference is that 3D particle systems use 3D meshes instead of sprites and 3D materials instead of 2D materials. Here we have a scene with Mr. G walking through a forest at night. And because it's a bit dark, Mr. G brought a torch along with him. But every torch needs a flame, and right now Mr. G's torch doesn't have one. The torch is in its own scene, so let's open up the torch scene. And we can see that the torch is just a simple torch model I made in Blender and a flickering omni light that helps selling the illusion that this is actually a torch. So let's make some flames now, and to do this, we are going to add a 3D particle system node. So we press Ctrl A to add a node, and then we type particles 3D. And similar to the 2D particle systems, there are two nodes available: CPU particles 3D and GPU particles 3D. And like in 2D, the CPU particles are less powerful and will not get any more updates in the future, so we are going to use the GPU particles 3D. Now let's drag the particle system a bit up, so its center is where the flame would be. And maybe let's hide the torch model for now, so it isn't in the way. Now we can add some particles to it. In 2D, particles always were sprites, but in 3D, particles can be pretty much any 3D mesh that we would like. We have a draw process setting here, where we can set up one or multiple meshes that our particle system will draw for each particle. In most cases, we will only need one mesh, but if for some reason we would need more than one, we have the option to do so. For our torch effect, I'd pretty much like to do it the same way as our fire in the 2D video, so I'm going to use a simple quad mesh with a flame texture applied to it. So let's add a quad mesh. And this is a bit large, so let's scale it down to about 0.25 meters. Now we want this to look like a flame, so let's add a material to it. We use a standard material 3D for this, and for the flame texture, I'm going to use a texture that I have prepared already, which looks like a little flame. So let's go over here to Albedo, and then we can just drag the texture into this slot. Now that doesn't really look like it's supposed to look. The spot around the flame should be transparent, but it isn't. And this is because by default, transparency is disabled for the standard 3D material. But we can fix this quite easily. We go up here to transparency, and then we set it to alpha. Now that looks a lot nicer. Now our flame looks somewhat grayish, and this is because by default the material is shaded, so it will react to light sources and will also have shadows on it, and this is something we don't want for our flame. Our flame is supposed to be its own light, so we go here to shading, and then we set the shading mode to unshaded, and then there will be no more shadows on our flame. Now let's set up the behavior of our particle systems. And like in 2D, the particle system is controlled by a particle shader. And like in 2D, we can either write our own particle shader or use a particle process material. Writing particle shaders is something we will have a look at in part 3, so let's use the particle process material for now. Now our particles start moving, but they are falling down, and that's not really how flames behave, so let's change that. The settings of the particle process material are exactly the same as in 2D, but they behave slightly different in 3D. Godot has a very nice documentation page about how these settings work in 3D, which explains all of these settings in detail, and even has some nice example images that show us what we'll get. There's a link to this documentation page down in the description. Okay, let's first fix the gravity, and we don't want our particles to fall down, but rather move upwards. So maybe just reverse the gravity. We can now also make the torch model visible again, so we can see how everything looks together. Now our flames are moving upwards, but it would be nice if they spawned over this whole upper part of the torch and not just at the center. Now we can set this up here in spawn position. And for our torch effect, a sphere shape would probably work nicely. And it's rather difficult to see where the sphere is, so let's increase the amount of particles to maybe 1000. And now we can see the sphere a bit better. The sphere is a bit too large, so let's decrease the radius to 0.1. Well, that's a tiny bit too small, so maybe 0.13. Yeah, that starts to look like a flame. It would be really nice if we got a bit more variety in our particle system sizes, so they don't all look the same, and we can fix this in the scale settings. If we set the min scale to maybe 0.8, and we leave the max scale as it is at 1, then we get a nice bit of variety in our particle sizes. Now we also want our flames to get smaller as they go up. And for this we can use this scale curve. So let's click here on scale curve and then select new curve texture. And now we have a curve control here, which allows us to control the scale of our particles. This works exactly as it works in 2D. The x-axis is the lifetime of the particle, and on the y-axis we can control how big the particle should be. We want our particles to start at full size, so we put the first point up here at 0 and 1. And now over time we want the particles to shrink, so let's drag the second point a bit down. This looks better, but the flames still go way too far up. We want the particles to disappear sooner, so let's just cut down the lifetime of the particles. And we can do this up here in the time section. A value of about 0.45 seconds should work nicely. And now our flames look much better. Next, let's add some color to our particles, so this actually starts looking like a flame. And we already did a similar thing for the campfire smoke in the first video, so we know that we can use a color ramp for this. Now let's go to Display, Color Curves, and here in the color ramp setting, we add a new gradient texture. That doesn't seem to be working. We should already see a color gradient on our particles, but they stay white. Why is that? Well, the reason is that the material that we have assigned to our particles does not know that it is used inside of a particle system. But this material is responsible for controlling how the particles look. So how does the color ramp from our particle system get into the material? In Godot, this works like this. Our particle process material calculates which color the particles should have right now, and then adds this information to the vertex color attribute of our mesh vertices. So for our particles to have the correct color, we need to tell the material to use this vertex color to determine the color of the particle. And to do this, we go down here to Material, And in the vertex color section, we select Use as Albedo. And now our particles show the gradient. That's great. So let's now set up the gradient. For a flame, the color usually is very dark at the beginning, and then the flame gets red, and then yellow, and then white. So let's add 3 more stops to our gradient here. We make a red one, and a yellow one, and a white one. Let's also add another dark gray one to simulate a tiny bit of smoke. And now we can drag these around until we get the look that we want. Yeah, and that looks pretty good. What I don't really like is how these particles pop in and out of existence. It would look a lot nicer if they faded in and out, but that's an easy fix. We can use the alpha curve right here for this. So let's click here and add a new curve texture. And inside of the curve texture, we add a new curve. And now we can set up the transparency of our particles over time, just like we did with the scale earlier. So we start with a transparency of 0, and then ramp up until 1, and then ramp back down to 0. And now our particles nicely fade in and out. That looks pretty good, and we could still spend a lot of time tweaking this to make it look even better, but for now I think this is good enough. So let's save the scene and go back to the main scene with Mr. G. That torch looks really nice, and the flicker of our light really sells the illusion that this is a torch. So let's try it out in game. We start the game, and for some reason the flame is not there. Why is that? It seemed to work in the editor, so why doesn't it render in the game? Well, the reason for this is that we draw our particles as 2D quads. And these quads have a front and a back side. And right now, the camera is behind Mr. G, and we see the back side of the quads. By default, Godot doesn't render the back sides, but if we turn the camera around, so it is now in front of Mr. G, we can see the flame because Godot renders the front sides of the quads. So how can we fix this? We could tell Godot to also render the backside of the quads, but this would still not work if we look at the flame from the side. So if I turn the camera here to the side, you can see how these quads really don't look like they should. So what we need is that these quads always face the camera. This is called billboarding, and Godot has built-in support for this, so we don't even need to program it ourselves. Well, let's close the game and go back to the torch scene. And billboarding is a setting on the material. So we need to go to our draw process and then select the material. And here we have a setting called billboard, which has quite a few modes. Now let's see what they do. So let's start with enabled. Now this somehow messed up our scale curve, and the particles no longer shrink as they go up. But we have this keep scale setting, which fixes this. Now the particles follow the scale curve again. Let's try to move the camera and see if it works. And that looks good. Okay, so what do the other modes do then? Well, let's try Y billboard. This looks very similar, but if we move the camera up, we can see that the particle's y-axis does not follow the camera. And this is probably more useful if you use the material for something like grass, where you don't want the grass to follow the camera's up and down motion. Now we also have particle billboard. This looks exactly like enabled, but it adds a few more settings if we want to have particle animations like for the smoke we did in the first video. So I think for our case, we can either use enabled or particle billboard, but because we don't need the particle animation, let's stick with enabled. So let's save the scene and run the game again. And now if we move the camera, we can always see the flame no matter where the camera is. This is great. Now Mr. G can take a walk, maybe over there to these trees. Well, that's not good. When Mr. G walks, the particles from the flame are left behind. And this is because the particles are spawned in world space and are completely independent of Mr. G. So when Mr. G moves, the particles stay where they are spawned, and this is not what we want, so how can we fix this? Well, let's go back to our particle system. And if we go here to drawing, we have a setting local coordinates. If we enable this, then the particles will be spawned as child of the particle system. So if the particle system moves, then the particles will move with it. Well, let's try this out. And this works great. Now the particles no longer leave a long trail behind Mr. G, but actually it would be really nice if the flame somewhat reacted to the movement of Mr. G. So we want a little bit of drag, but we don't want the particles to stay behind Mr. G. How could we do this? 3D particle systems in Godot can use particle attractors to attract or repel particles. And this is something that 2D particle systems can't do right now. But since we're in 3D, let's try to use this feature to simulate a bit of drag on our flame. To do this, we add a particle attractor to the torch, and this attractor drags behind Mr. G and pulls on the particles of the flame. But we don't want the particles to be dragged too far out, so our attractor should not move too far away from the torch. When Mr. G stops moving, then the attractor moves back to the center of the torch and the flame goes back to normal. So first, we need a center point for the attractor, and this should be right on top of the torch. So let's use a marker 3D for this, so we can see the node even if it's not selected. We press Ctrl A to add a new node, and then use a marker 3D. Let's drag this up a bit so it's right on top of the torch. And now we can add a particle attractor as a child to this marker node. So let's press Ctrl A again and search for Attractor. And here we have a GPU Particles Attractor Sphere 3D, which is a particle attractor that attracts particles in a sphere around it. Let's add this node, and now we get a little sphere shape here, which shows us the area where the particles are attracted. I think the default size of 1 meter is just right for what we need, so let's keep that. Now we have two more properties, strength and attenuation. Well, let's set the strength to something like 6, and let's see how it works. And we see that our flame suddenly becomes much smaller because the particles are dragged towards the center of the attractor. And now if we move the attractor away from the center, we can see how the particles follow the attractor, and it looks like the flame is blown by the wind. But if I drag the attractor a bit more, we can also see that the effect is less and less strong the further away the attractor gets. We can control this with the attenuation setting. Right now it is set to 1, which means that the strength of the attractor is the highest in the middle and then falls off towards the edges. So if I move the attractor a bit closer to the torch, we can see that the effect becomes stronger. If we set this to a -1, well, then the effect is reversed, and now the attractor is much stronger at the edges and falls off towards the center. For our case, we want the effect to be about the same strength everywhere, so let's set this to 0. Now we have the attractor set up, but we are going to need a little script to move the attractor behind Mr. G. We want this to be as simple as possible, so we are going to let Godot do the most of the work for this. So instead of reacting to the movements of Mr. G directly, we set up the attractor to not follow its parent node. And we can do this with the top level setting down here in the transform section. Now Godot will not consider our attractor to be a child of the marker node, and it will not move with the marker node. So if Mr. G moves, then the attractor will stay where it is. And all we need to do is write a small script that drags the attractor back to the marker node. So let's add a new script to this marker 3D node. And we call it maybe flame_drag.gd. We're going to need a few variables for this script. First, we need a reference to the particle attractor so we can actually move it. So let's right-click the attractor and then select access as unique name. And then we can hold Control and drag the node into our script. Let's rename this to Attractor. And let's also add a type hint to it so we get a nice auto-completion. Next, we're going to need a variable to store the maximum distance the attractor should be from the torch. Now let's call this max distance and set it to 0.5 meters. We export this variable so we can later tweak the behavior without having to change our script. Now we can add a process function to our script where we can put the actual logic. First, we need to make sure that the attractor is not further away from the torch than our allowed maximum distance. So let's first calculate the distance from the attractor to our marker. And Godot has some built-in functions for this, so we can just use a var current distance. This is a float. And we just say attractor global position, distance to our own global position, right? This script is attached to the marker, so this refers to the global position of the marker. So now let's check if the marker is too far away. So if the current distance is greater than the maximum distance. And if this is the case, we want to move the attractor closer to the marker. We can do this by calculating the direction from the marker to the attractor, and then calculate a point in this direction that is max distance away from the marker. So let's first calculate the direction from the marker to the attractor. For direction, this is a vector 3, and this is our own global position, direction to attractor global position. So now we have a direction that points from the marker to the attractor. And now we can set the attractor's global position to a point that is max distance away from the marker in this direction. So attractor global position, and this is our own global position plus the direction times max distance. And now we can try this out, but before we run the game, it would be very useful if we could see our attractor in the game. So let's add a small sphere here as a child to the attractor. So Control A to add a node. And we're going to use a CSG sphere 3D. And let's scale this down to 0.1 meters. And now we can see where our attractor is. Nice. Okay, time to run the game. And if we move Mr. G a bit around, we can see how the flame is dragged towards our attractor. This looks really nice. Now we just need to make sure that the attractor moves back to the center of the torch when Mr. G stops moving. So let's go back to our script and add this logic. Our attractor should not immediately pop back to the center though, so we will need some speed variable for our attractor. So let's add a new export variable for this, so we can tweak this later. And we call this variable speed. This is a float, and let's go with 8 units per second for now. Now we can add the code that moves the attractor back. And this is really easy because we just need to move the attractor towards the marker's global position. And we can use Godot's move toward function to do this. So we just say attractor global position. And this is the current global position of the attractor. And on this position, we call move toward and give it the global position of our marker. And then we can give it a speed, which is our speed variable from up here. And we multiply this with delta, so we get a nice smooth motion. Well, let's try this out. We start the game. And let's move Mr. G a bit to the left and to the right and see if that works. And that works nicely. However, when the attractor is at the center of the torch, then the flame is still tracked towards the attractor and becomes a little bit smaller than it is when the attractor is on the left or right. And this is not really what we want, so let's go back to the script and fix this. An easy way to fix this is to control the strength of the attractor. If we look at our attractor, we can see that its strength is now set to 6. So we could set the strength to 6 when the attractor is at the outer border, and then gradually reduce it to 0 when the attractor is at the center. And for this, we need to be able to set the maximum strength in our script, so let's add another export variable for this. So we add a variable max strength, and this is a float, and we set it to 6 because we know that is a value that works quite nicely. We have already calculated the current distance in our script, and we know the maximum distance, so we can quite easily calculate the strength of the attractor. We just take the max strength, and then we multiply this with the ratio of the current distance to the max distance. So when the attractor is at the center, then the current distance is 0, and our strength will be 0. And when the attractor is at the outer border, then our current distance is max distance, and the strength is max strength because this right term will become 1. So let's try this out. We start the game again, and we move Mr. G around a bit. And this time the flame keeps its size when the attractor is at the center of the torch. This looks really nice. In almost every 3D game, you will find some form of rain, and while a basic rain effect is quite simple to set up in Godot, things get a lot more complicated if we want our rain to interact with the environment. But first, let's set up a basic rain effect. So we press Ctrl A and add another GPU Particles 3D node to our scene. And the rain should fall from the sky, so let's move the rain up by about 20 meters. Now we can add our process material, and we also need a draw pass so we can actually see our particles. Let's maybe start with little spheres, so we can set up our particles, and then we change the mesh later to make it look more like rain. So let's add a sphere mesh, and we set the height to 0.05 and the radius to, well, half of it, so that's 0.025. And now we can see our particles and we can set up how they should behave. First, let's set the particle amount to maybe 1000 so we can better see what's going on. And now we need a nice emission shape. So let's go with a ring shape here. And we set the radius to 10. Now we see that this ring has the wrong orientation, so we need to change its axis. We want it to be oriented along the y-axis. So we set this axis to 0, 1, 0. Our particles don't reach the ground yet, so let's increase their lifetime to maybe 5 seconds. Great. Let's see how this looks in game. We start the game, and our rain is not visible at all. Why is that? Well, similar to 2D particle systems, 3D particle systems also have an area that controls whether the whole particle system is visible. If we select our rain particle system, we can see this cube around it. And this is called the visibility AABB, which is short for axis aligned bounding box. This box must be visible on screen for our particles to be visible. We can change its size here in the drawing section. So let's increase its height to maybe 20 meters and let's move it down by 20 meters so it touches the ground. Now let's play the game again. And now the rain is visible, but it takes a while to get going. We already know how to fix this from the 2D video, so let's go up here to the time section and set the pre-process setting to maybe 10 seconds. And if we start the game again, the rain is in full spin immediately. Great. Now our little spheres don't really look like rain, so let's change that. I think using particle trails would work really well on this rain effect, so let's go over here to the Trails section and enable Trails. Well, that doesn't seem to be doing a lot, and the reason for that is that particle trails in 3D don't just work out of the box with any mesh. They need a specialized mesh to work with. So let's go back to our draw passes and see what options we have. If we open the dropdown, we can see a bunch of meshes, and down here we have two options: tube trail mesh and ribbon trail mesh. Well, let's try the tube one first, and our particles disappear. Well, there seems to be a bug in Godot, but we can fix this by just switching the trails off and on again. And now we can see that our particle trails are rendered as cylinders or tubes. Well, this is not really what I would like to see for the rain, so let's try the ribbon trail mesh. And well, this seems to produce some kind of cross. If we now put a nice transparent texture on this, this could actually look like a rain streak. So let's add a material to this. And I have prepared a little streak texture here. So we can open up the albedo section and drag this texture in. It's not really visible right now, and this is because the texture is mostly transparent and we haven't yet enabled transparency for our material. So let's go up here to transparency and then set it to alpha. And now we can see our rain streaks. But it still looks a bit weird. If we rotate the camera a bit around the particles, we can see the same problem that we had with our flame. When the camera is on the wrong side of the particles, we just don't see them because Godot will by default not render the back side of these particles. We could fix this with billboarding again, but this time we're going to use a different approach. There's a setting called Cull Mode here in the transparency section, and this controls how geometry is rendered. By default, it is set to back, which means that Godot will not render anything that is facing away from the camera. We have two more options, front and disabled. A front will do the opposite of back, so it will only render geometry that is not facing the camera. This is also not what we want, so we set this to disabled. And now we can see our rain streaks from all sides. But they still don't look right. They should render as long streaks, but they are chopped up in little sections. And if we look here at our particle node, we can see that Godot shows us a little warning. Trails enabled, but one or more mesh materials are either missing or not set up for trails rendering. Well, we definitely have a material, but how do we set it up for trails rendering? Well, this setting is a little bit hidden. We need to go down to the material and then to the transform section. And here we have a checkbox, use particle trails. And if we click that, our trails now look like they should. Except that our particles have now become very dark. If we rotate our camera around, we can see that the side that faces away from the light is now lit, while the side that faces the light is dark. I've reported this to the Godot developers, and this has been confirmed to be a bug, so we cannot fix this right now. However, because we are only going to do a stylized version of rain, we can probably get away with just disabling light and shadows for the rain particles. So let's do that. We go up here to shading, and then we set it to unshaded. And now our rain particles are white, no matter from where we look at them. Now the rain particles are a bit too large, so let's change the size of our ribbon mesh to maybe 0.05 meters. That's still thicker than in reality, but it works for the effect that we want to achieve. Now we need our main ingredient for every particle system, and this is variety. So let's start with particle sizes. So we go to our process material and then display scale. And let's pick 0.1 for the minimum scale, and we leave the maximum scale as it is. And now we can see that we get thicker and thinner rain streaks. This looks much better. Our trails are somewhat long, so let's cut the lifetime of our particle trails here in the trails section to maybe 0.1 seconds. Yeah, that looks better. The particles could move a bit faster though, and it would also be nice if they wouldn't all fall straight down. So let's fix that here over at spawn and velocity. And let's increase the initial velocity to maybe 10. Now, our velocity direction vector is 1, 0, 0. So now all our particles move to the right. And we want them to move downwards, so we set the y component to a -1. And let's also reduce the x component a bit so the rain doesn't have a 45-degree angle. Now the rain falls down, but the pattern looks more like snow because it moves in all directions. We can fix this by reducing this spread setting here. If we use something like 5 degrees, then all the particles roughly go into the same direction, but we still have a little bit of variety. And this looks much better. To make it look a bit more like water, we could also make the rain a bit more translucent and maybe even change this translucency over time. We already know we can do this with an alpha curve, so let's go to Display, Color Curves, and then in the alpha curve, let's add a new curve texture and a new curve to it, and then let's set up the curve. We start at 0 and then maybe go up a bit to 0.25 and then back down to 0 and another one up to 0.25 and back down to 0 and maybe add a third one just up to 0.10 or so, and finally we go back to 0. But it looks like our curve has absolutely no effect. And the reason for this is the same as with the flame. Our material doesn't know that it is used inside a particle system, so it doesn't pick up the alpha changes from our particle process material. And to fix this, we go to the material and then vertex color and set this to use as albedo. And now our rain particles fade in and out. But the effect is rather subtle, and why is this? Well, if we hide the terrain, we can see that the rain lifetime is a lot longer than it needs to be, and this curve that we have just created is played out over the whole lifetime of the particle. So we need to cut the lifetime of the particles down so that their lifetime ends just after they have hit the terrain. So let's go up here to the time section, and then let's drag the slider down until the particles disappear just after they have hit the terrain. So 1 second is too short and 2 seconds is too much, so let's go with something in the middle. Now this looks pretty decent, so let's check how it looks in the game. We start the game, and this looks pretty nice, so let's have a walk with Mr. G in the rain. Well, we only have rain over this particular spot of our world, so Mr. G can just walk out of the rain. Well, that's not good, so let's maybe increase the area of our particle system. We go to our process material and then spawn, position. And now we can increase our spawn ring, and maybe let's go with 500 meters. And that should be enough to cover the whole area. Well, except that 1,000 particles really are not enough. So how about 10,000? Well, better, but still not enough. Well, let's ramp it up to 50,000. That looks about right. Well, let's start the game again. Now we have rain over the whole area. Great. But isn't 50,000 particles a bit much? Well, let's have a look at the performance. To see how well we are doing, let's open up the visual profiler. And right now, we spend between 2 and 4 milliseconds per frame for rendering, which is about a quarter of our budget if we aim for 60 frames per second. Let's see how that changes when we reduce the amount of particles. So let's go back to our particle system and let's reduce the amount of particles to 15,000. And to get a similar visual appearance, we also reduce the radius of our spawn ring to 100 meters instead of 500. Now let's start the game again and let's have a look at the profiler. And we can see that there is not much of a difference. In general, if our particle geometry is simple, like a quad or a ribbon trail, then Godot can really render a lot of particles without much overhead. But let's say we have a very large open world and want to make rain for that. At some point, we will need to have more particles than we can fit into our rendering budget, so just increasing the particle count and the area isn't going to work. But we can move the particle system with Mr. G, so Mr. G has its own personal rain cloud that follows him everywhere. There are a few different ways to do this. If possible, it would be really nice if the player doesn't need to know about the rain. So instead of letting the player move the rain, let's have the rain follow the player. And we can do this with a custom script. So let's add a new script through our rain particle system. And this is going to be a simple follow script, so we name it follow.gd. Well, this script is pretty generic. It will work for all node 3Ds, so we can just change the extends line up here to node 3D. Now we need a reference to the node that we want to follow. So let's export a variable for this. Export var target. This is a node 3D. Now our rain particle system should always be 20 meters above Mr. G, so we need an offset which we can add to the target's position. Let's also export this so we can tweak this offset in the editor if we need to. So export var offset, this is a vector tree, and we initialize this with 0, 20, 0. And now we just need a small process function that moves our particle system to the target. So we add a process function. And first we need to check if the target is still valid because it could have been freed or maybe we forgot to set it. So it's always a good idea to be defensive in our code and check for these things. So if not is instance valid target, then we return. And now we can just set our own global position to the target's global position plus the offset. Well, let's select the player as the target in our editor. And we're ready to go. Let's start the game. And maybe zoom quite a bit out so we can see the whole rain field. And now let's take a little walk. And our rain follows Mr. G. Nice. We have a little wooden shelter here in our world, and Mr. G would like to take some shelter from the rain. But if we move Mr. G inside of the shelter, we can see that our rain particles just fall straight through the roof. How can we fix this? Well, we can use Godot's particle collision system to make our particles disappear when they hit the roof. To better understand how particle collisions work in 3D, I have prepared a little particle collision test scene. Here we have a simple setup, a small ground plane, our shelter from the main scene, and a copy of Mr. G, so we have a size reference. We also have a particle system that spawns some particles that fall down. And right now, these particles fall through the roof and the ground, like in our main scene. To get some particle collisions going, we first need to activate collision in our process material. So we go to the process material, and here in the collision section, we can change the collision mode. We have three options: disabled, rigid, and hide on contact. We want our rain particles to disappear when they collide, and for this we will use the hide on contact option. But even with hide on contact enabled, the particles are still going right through everything. And this is because the particles need to know what they should collide with. And like in 2D, particles do not interact with Godot's physics engine and their physics colliders. So even though our shelter and the ground actually have some physics colliders, the particles will not collide with them. In 2D, we used a light occluder 2D node to define what the particles should collide with. And in 3D, there's a similar system, but it's a bit more complicated. A very simple way to get started is to use the GPU Particles Collision Box 3D node. Well, let's add one of these. So Control A, and then we search for collision, and we use this collision box node. So now this node is a simple box that defines a collision volume. Well, let's change its size to 16 by 2 by 16 meters. And let's drag it up a bit so it's above our shelter. And we can see how stuff collides. Except that our particles still don't collide with the box. Why is that? Well, do you remember how our rain wasn't visible at first because we needed to set up a visibility AABB for our particle system? Well, this AABB does not only control whether the particles are visible, it also controls the area in which the particle system will check for collisions. If we select our particle system up here, we can see that its AABB doesn't quite reach down to the collision box that we have just added. So let's increase its height to maybe 24 meters. And let's also adjust the Y offset to be negative 24 meters. And now our particles collide with the box and disappear. Great. So let's delete this collision box and see how we can set up proper collision for our example setup here. I have already created a collision box for the ground plane. So let me quickly hide our meshes. And we can see that the particles now collide with the ground plane and disappear. Except that some of them are still falling through the ground. Why is that? This is an effect called tunneling. Our rain particles start about 25 meters above the ground. And they are pulled down by gravity and get faster and faster. So when they hit the ground, they will have a velocity of about 22 meters per second. Now our particle system will only simulate the particles at a fixed rate. And by default, this is 30 frames per second. So if we have a particle that moves 22 meters per second, then the particle will move about 0.7 meters in every frame. But our collision box here is only half a meter thick. So a particle might be above the collision box in one frame and below the collision box in the next frame. So for the particle system, it looks like that this particle has never collided with the ground, and this is what we call tunneling. There are two ways in which we can fix this. First, we can make the collision box thicker. So if we make it 1 meter thick, then there's no way for a particle to tunnel it because it only moves with 0.7 meters per frame. So it must eventually end up inside of the collision box. The second way in which we can fix this is to increase the simulation rate of our particle system. Let's set the thickness of our collision box back to 0.5 meters. And now we can increase this fixed FPS setting here in the time section. So if we set this to 60, then our particle will only move about 35 centimeters within a frame, and this is less than the thickness of our collision box. And we can see how this fixes the problem as well. However, if we make our collision box really thin, like 5 centimeters, we can see that the particles tunnel again. And of course, we can counter this by increasing the FPS even more. So we have reduced the thickness to 1/10 of its original thickness. So we would need to increase the frame rate by a factor of 10. So if we enter 600 frames per second, it will actually work in this small example. But in a real game, the computer may not actually be able to simulate particles at this rate because it's either not powerful enough or simply has a lot of other things to do. So for your own game, you will need to find a working compromise between the thickness of the collision box and the simulation rate of the particle system. Okay, so let's change the collision box back to 0.5 meter and set the frames to 60. And let's also show our meshes again. So now we can see that while the ground blocks the particles, our shelter still doesn't. So we would need to add another collision box for our shelter. But this is a bit cumbersome, especially if we have a lot of objects in our world, and we would need to add a collision box for every object that we want our particles to collide with. Also, our main scene has a terrain, and we cannot use a simple collision box for a terrain. So how can we fix this? I have prepared a second setup where we have a simple terrain and again our shelter and Mr. G. There's another node which we can use for this setup, and it's called GPU Particles Collision Height Field 3D. So let's press Ctrl A to add a node, and we search for height. And now we can add this height field 3D node. Now we get this little box here, which is the size of the height field node. Now inside of this box, the node will automatically look at all geometry from the top and then generate some collision information from it. The good thing about this is that this just works for any piece of geometry that is inside of this height field box, and we don't need to add a collision box for every object in our world. So let's increase the box so it covers everything. And if we pull over our particle system, we can see that the particles now collide with both the shelter and our terrain without any additional setup. We can also move this height field with our player, and it will automatically update the collision information. This really saves a lot of work. However, there is also a drawback to this. The height field just looks at the scene from a certain direction, and it cannot model overhangs or caves. I have a second particle emitter here, which emits horizontal particles. And we can see that these particles collide with the empty space below the shelter, even though they should go right through it. And this is because for the height field, everything that is past the first thing that it sees is considered solid. So what else can we do? Well, we could use 5 collision boxes to model the shelter's roof and the beams. And this would work, but it's quite a bit of setup. And what do we do if our object isn't nicely rectangular like our shelter? For these things, Godot offers another particle collision node, the GPU Particles Collision SDF 3D. Well, these nodes are all a mouthful. I have a third setup here with the shelter and a few trees behind the shelter. And now let's add the node. Ctrl A to add, and then let's search for SDF. And then we add this node. And now we can see that this node has a box similar to the height field node. So let's first increase this box so it fits around the shelter and the trees. Now, how is this different from the height field? Well, instead of looking at the scene from the top, this node looks at the scene from all sides and generates a signed distance field from it. A signed distance field is just a bunch of numbers that tell us how far a point is away from the surface of a thing. So if we look at this box, we can see that it is subdivided into a lot of smaller boxes. And for each of these smaller boxes, the node calculates how far it is away from the nearest object. And then the particle systems can use this information to calculate if they have collided with something or not. So let's move our particle system over. And we can see that nothing collides. Why is that? Well, signed distance fields are somewhat expensive to calculate, so the node will not calculate it on the fly. Rather, we need to bake the signed distance field first. And to do so, we first select the node, and then we can click the Bake SDF button up here. Now a dialog opens, and it asks us to save a texture. And this texture is what comes out of the baking process, and the texture contains the signed distance field data. This is a 3-dimensional texture, so it can become quite large depending on the resolution that we set up on the node. For now, let's keep the default name and save the texture. But we get an error message No faces detected. Check whether there are visible meshes matching the bake mask. Well, that is strange. We surely have meshes inside the SDF box, so what is the problem here? Well, this is actually another bug in Godot 4.2. This SDF node only detects meshes that are on the same level or below the node itself. So right now our SDF node is here in its own collision branch. But if we move it one level up, so it is now at the same level as the shelter and the trees, and then hit the bake button again, and save the texture, then the baking works. And if we now click on the texture property of our SDF node, we can see the texture that was generated. And this is a 3D texture which has a bunch of layers, where each layer is a slice of the sign distance field. And if we use the spinner box here, we can scroll through the slices and see how the sign distance field looks. For example, we can see the form of our shelter here, and here we have our trees. And this can be quite useful when we try to debug why particles are not colliding with something. Now our SDF is baked, but you may have noticed that the particles are still falling through the shelter. Why is that? Well, this is another bug in Godot 4.2. After we have baked the SDF, we need to reload the scene to make it work. So let's save the scene and then reload it up here in the scene menu with reload saved scene. And now we can see that the particles collide with the shelter roof. And if we drag the other particle system over, we can see that the particles now probably go through the shelter and are not blocked by it. But we can also see that our particles seem to go through the trees, even though they should collide with them. Well, this is another bug in Godot 4.2. The SDF node will only collide when the particle system's bounding box was over the SDF node when the scene has been loaded. This is only in the editor, so it will work in your game, but it can be really frustrating when you set up your scene and try to figure out why it's not colliding. We can fix this again by reloading the scene. So scene, reload, saved scene. And now our particles collide with the trees as well. So if your particle collision behaves strangely, there's a good chance that reloading the scene will fix it. If we move our camera behind the trees, we can see that these big particles make it through these rather small holes in the tree. And this doesn't look very realistic, but how can we fix this? Well, particles themselves don't have all these collision shapes that normal physics objects had. Instead, particles only have a single collision shape, a sphere, because a sphere can be calculated very quickly. And we can set up the size of the sphere here in the collision section of our particle system. Here we have a setting collision base size, and this is the diameter of the collision sphere of each particle. And right now it is set to 1 centimeter, even though our particles are a lot bigger. If we look at our mesh, we can see that one particle is 60 centimeters or 0.6 meters in diameter. So let's change the collision base size to 60 centimeters as well, so it matches the visual size of our particles. And now we can see that the particles are blocked a lot better by the trees. So now that we know how to set up particle collisions, we can return to Mr. G and finally make a working shelter for him. Well, let's go back to our main scene. And now we can set up the collision for our rain. In our case, I think that a height field collision works best because the rain comes from the top. And the height field should move with the rain. And because we already have set up the particle system to follow the player, we can simply make the height field a child of the particle system. And this way it will move with the particle system. So let's select the particle system, then Control A to add a node, search for height, and there we have it. Now, how big shall we make this height field? Right now, our rain has a radius of 100 meters. However, we don't really need our particles to collide with the ground 100 meters away from Mr. G. This is so far away that nobody will really notice if the particles fall through something there. Let's go with a size of 50 by 30 by 50 meters. And now the height field is a bit too much above the ground, so let's go down to transform and move the height field down by about 15 meters. Now we only need to set up our particle system to actually have collision, and we're done. So let's first go to the process material and set the collision mode to hide on contact. And we have already learned that for collisions to work, the visibility AABB must be big enough to cover the height field. So let's set up the size and the offsets so it matches the size of our height field. Now everything is set up nicely, so let's start the game and see if it really works. Well, let's walk Mr. G under the shelter, and we can now see that the shelter actually blocks the rain. Great! So now that we have working rain, it would be nice if we saw some little ripples on the ground where the rain hits it. We already did a similar thing in 2D, and it works pretty much the same way in 3D. We're going to use a sub-emitter for this. So let's first hide the rain particle system while we work on the ripple effect. And then let's add another GPU particles 3D node. So Control A, search for GPU, and we add this node. And let's move it a bit away from Mr. G so we can see what's going on. And now we add a process material, and as a draw path, we use a simple quad mesh. Now the meshes fall down, and this is because the process material comes with some gravity by default. So let's go to acceleration, gravity, and then set the gravity to 0. We also only need one particle right now, so let's set the amount to 1. And back to our mesh. This mesh should point upwards. So let's go to draw path again. And here we have an orientation setting. Upwards is the y-axis, so we use phase y as orientation. And now our quad mesh lies flat on the ground. Now, this doesn't really look like a ripple, so let's add some texture to it. First, we need a material, so let's add a standard material. And then we can go here to albedo and drag in a drop ring texture. Now this looks a bit weird, and again, this is because we haven't yet set up the transparency. So let's go up to transparency, and then we set this to alpha. Great, now we have a ring, but it is a bit static, so let's add some life to it. First, it would be nice if the ring would start out small and then grow over time. Well, we already know how to do that. Let's go over to our process material, and then display, scale. And to change things over time, we use a scale curve. So let's add a new curve texture. And now we can edit the curve. We start at 0 and then grow the size up to 1. Well, that looks nice, but it's maybe taking a bit too long. So let's reduce the lifetime of our particles to maybe 0.6 seconds. That's better, but it will probably look even nicer if the rings have different sizes. So let's go back to the scaling settings and let's bring the minimum scale down to 0.1. This way we get a bit more variety. Another thing that isn't great is that this ring pops in and out of existence, and it would look nicer if it faded. We already have done this for the rain, so let's go to display, color curves, and add an alpha curve. And now we can set up how the alpha should change over time. Let's start with 0 and then go up to 1. And at the end, we go back to 0. And nothing happens. We had the same problem when we made the rain, so you probably remember how we fix it. Well, we need to go to the material of our draw path and then to vertex color and then set use as albedo. And now we can see that the rings fade in and out. And maybe we could make the rings a bit more transparent so this effect is a bit more subtle. So let's go back to our alpha curve and reduce the maximum to maybe 0.5. Okay, that should about do it. So let's cut it here and let's set this up as a sub-emitter for our rain. Maybe let's also do some renaming so we know which particle system is which. So we name this particle system drops and our rain particle system rain. And then let's make the drops a child of the rain particle system so everything is nicely organized. Well, let's also reset the transform so we have all the particles in one place. Okay, now let's select the rain particle system. And up here in subemitter, let's select our drops particle system. We also need to go down to the process material and down here in the subemitter section, let's set the mode to add collision because we want the rings to appear whenever the rain hits the ground. Again, this works exactly the same way as in 2D, but like in 2D, we don't really see our drops. And do you remember what the problem was there? Well, the amount of particles in our drops particle system limits how many drops we will actually see. And right now, this is set to 1. So we have about 15,000 rain particles, but only 1 drop particle. So let's increase the amount of drops to maybe 5,000. But this doesn't seem to work. Why is that? Well, let's quickly hide the terrain. And there are our drops. Well, let's move the camera a bit down so we can see it better. Oh, wait, now the ripples have disappeared. Why is that? Well, let's move the camera back and they are visible again. Now, what is going on here? Well, if you look up here, you can see the visibility AABB of our subemitter. And when I move the camera down, then this AABB will not be visible to the camera anymore. And that is why our ripples disappear. So if we use subemitters, they don't magically inherit the AABB of their parent emitters, but always use their own AABB. So let's give our subemitter the same AABB as our rain. So let's go to rain. And here in the drawing section, we can right-click on the visibility AABB and then select copy value. And then we go back to the drops, right-click on the visibility AABB and select paste value. And now our rain and our drops have the same visibility AABB. Our ripples are visible again, and we can fix the other problem that we have. Why are they below the terrain? Well, remember when we looked at collisions that we had this problem that if we didn't make our collider thick enough that the particles would tunnel it. Well, this problem is related to it. The collision point that Godot calculates actually depends on the speed of the particle. So if the particle is faster, then the collision point will be calculated somewhere inside of the terrain. And we can fix this in 2 ways. We can increase the FPS of our particle system, and this way the particles move less in a single frame, and the collision point will be calculated more accurately. So let's try 60 FPS. And now we can see that the collision point moves up a bit, because the particles move less in a single frame. But if we enable the terrain again, we can see that the collision point is still below the terrain. Now, we could try to increase the frame rate even more, but this is not really feasible for most projects. So what else can we do? Well, remember how we prevented the particles from going through our trees by increasing their collision size? We can do the same thing here, and if we tweak it correctly, it will look like the drops are on the terrain. So in the collision section of our rain particle system, let's set the collision size to about 1 meter. And now we can see that most drops are on top of the terrain. Unfortunately, this is really just a workaround because the drop collision point depends on the speed of the drops, and the speed can vary slightly if we have differences in terrain height. So some drops will appear below the terrain, while some other drops may appear slightly above it. And ideally, this would be something that Godot figures out automatically, but right now we just have to work around it. We can make our drop rings a little bit more translucent, so it is not as noticeable. So let's go back to our drops particle system. and then to the process material, and then to the alpha curve. And then let's reduce the maximum to maybe 0.25. And now we can see that the drops are a bit more subtle. And let's start the game and see how it looks there. And this looks pretty nice. There's another problem though, and it's another one that we cannot fix right now. We can see that drop rings also appear on Mr. G. And if we walk near the trees, we can also see drop rings appear on the trees. And this is not really what we want. However, there is currently no way to prevent this. We can neither tell our height field to exclude the trees, nor can we tell the rain particle system to only run the sub-emitter on terrain. So right now we either need to live with this problem, or we just need to disable the drop rings completely if we find this to be too distracting. In this video, we had a look at how 3D particle systems work in Godot. We learned that in general, 3D particle systems work very similar to their 2D counterparts, but have some key differences. We learned that 3D particle systems use 3D geometry rather than sprites, and also use 3D materials. And we learned that this setup requires some additional steps to get things like transparency and billboarding to work. We learned that 3D particle systems can use particle attractors to move particles, and we use this to create a wind drag effect on our torch flame. We learned how to create particle trails with tube and ribbon meshes, how we need to set up the 3D material to properly work with trails, and we used this to create a stylized rain effect. We then had a look at how particle collisions work in 3D, and how we can use simple collision boxes, height fields, and sign distance fields to make particles collide with the environment. We also learned how we can use increased collider sizes and tweaks to the frame rate to make the particle collision more accurate. Finally, we had a look at how we can use subemitters to create additional effects like ripples on the ground when the rain hits. We learned that subemitters work in the same way as in 2D, but that the limited accuracy of particle collisions can cause some problems if we want to create effects that spawn particles on collision. Godot's 3D particle systems are quite a bit more complex than their 2D counterparts, but with a bit of practice and experimentation, you can create some really cool effects for your game. I hope this second part of our particle series has been helpful. In the final part of the series, we will have a look at particle shaders and how we can use them to create effects that are beyond what the particle process material can do. If you have any questions or want to share something you have learned about 3D particle systems, please leave a comment below. If you liked this video, please give it a thumbs up and maybe consider subscribing to the channel to get notified when new videos are posted. Thank you very much and happy Godotneering!